Sorry to Bob for giving him the bank holiday slot. But if everyone can just sort of prop open their brains with matchsticks for another 45 minutes, this really is the last lap. So our last speaker is Bob Plant from the University of Reading. So Bob's going to talk about issues with convection and suitable framework.
Okay, thank you. I think it's a fair comment to say that there's a kind of general dissatisfaction with parameterization schemes. That doesn't seem too uncontroversial a statement to make. And I think probably the most problematic is kind of seen as being the convection parameterization. Okay, so there are a lot of kind of very stubborn systematic errors that have been in all of these models for many, many years that we think are associated with the convection. So what I'm going to do today is kind of talk about the convection scheme. And it's a parameterization. So parameterization will contain some assumptions and approximations, possibly quite brutal ones. Okay. And I guess in a sense these are the kind of brutal things that offend me particularly, right? They're not necessarily the particularly brutal things that offend anybody else, but these are the things that there's some kind of quite strong assumptions that going into here that I want to just back away from and see what happens. Okay. So in particular we're going to a traditional convective parameterization will be a built model. It will assume that there are many, many clouds in the grid box. These clouds will not be interacting with each other. They will all be independent. And the subgrid will be kind of slave to the resolve scale in the sense that we assume that the subgrid is going to be kind of in balance with the instantaneous and local forcing. Okay. Now, all of these assumptions are kind of, to say the least, contestable. Okay. They're quite strong assumptions on what we're doing. And what I want to do is just kind of roll back from some of these things, see what kind of framework we then end up with, and then we can kind of assess whether the standard framework is still a reasonable one. Okay? So I want to roll back in a way where the kind of traditional picture is still going to be a limiting case of this kind of system I want to look at, and we can assess whether that limit is going to be a sensible limit to be looking at. Okay. So the outline kind of says it speaks for itself, really. First of all, I kind of have to introduce you to the kind of basic framework of a traditional convective parameterization. And as I say, we'll move away from each of those assumptions and see what kind of system we're looking at now. And let's just see what we can learn. Okay, so let's start with a kind of traditional convection parameterization. So this is the kind of figure 1 of the classic paper by Arakawa and Schubert, and anybody else writing their scheme in 2010 is not going to start from a very different figure. Okay, so we've got this large area of space. You can kind of imagine this as being our grid box, if you like, and inside this box we kind of imagine that we're going to characterize the convection as an ensemble of clouds, so it's kind of a geometrical construct, if you like. Okay, so we assume things are going to be reasonably well mixed inside the cloud, so that we can characterize variables inside the cloud with just a number, with the typical temperature inside the cloud, and they're going to be embedded in an environment which is kind of tolerably uniform in the horizontal. So we're going to characterize, again, kind of typical temperature at any point in the horizontal, not worry too much about whether we're near to one cloud or another. And all these clouds are going to look different, and they're going to see them at different stages in their life cycle. Okay, so that's our kind of picture of what's going on. Now, one thing we're going to need is some kind of model of what a cloud kind of looks like. It's a kind of coherent vertical structure, and we have to say something about what the vertical structure is. So, embedded in all this is some kind of cloud model. So kind of here's our cartoon of a cloud. It contains some sort of updraft, all sorts of kind of processes, microphysical processes going on in there. It's kind of exchanging, it's kind of turbulent exchanges with its environment, which we kind of imagine as being some entrainment and detrainment, essentially some mixing of the kind of cloud properties and the environmental properties, and it'll stop where it's kind of the buoyancy runs out, and that will the ascent here will force some large-scale subsidence. Now, essentially, what we mean by everything looking kind of tolerably uniform and well mixed inside the cloud and outside the cloud is that this thing, the thing we want to predict, which is kind of the subgrid flux of some intensive variable chi, let's say the temperature or the moisture, we're going to assume that's kind of well described, reasonably well described by an approximation like this, where we sum over all the clouds, we look at the amount of mass transport in the clouds, and we take the difference between the variable inside and outside the cloud. Okay, so the mass flux is just going to be a product of density, fractional area occupied by this cloud, and vertical velocity in the cloud. Okay. So in this kind of framework, that becomes a kind of key variable. We really want to understand what is this mass flux.
That's the upward mass flux and not the down.
That's right, yes, yeah. This is the upwards inside each individual cloud. Yeah. Okay. So it seems to me that most of what's happened in convective parameterization in the last 30 years has been trying to get a better model of this. Okay. Insofar as we have had successes, it seems to me this is mostly where it's happened. Okay. But I'm going to take that as read today. I'm going to assume we've got something called a cloud model, and the cloud model will give me certain coefficients. Because you can build various plume models depending on how complicated you want to make your microphysics and so on and so forth. But actually the hard part of this is that your cloud model you get from integrating up from cloud base. Okay? And the part that you really don't know is what's the lower boundary condition for this integral. What is the mass flux at cloud base that starts the whole process off? Okay? That's what's known as the kind of closure problem for this. And yeah, and that is the kind of, no one's really had much success or much, there weren't really any kind of good ideas kind of over the last 30 years or so. That's a bit harsh, but there's not really, to me that's where the big problem is. Okay. Now typically the assumption is that the convection is being forced by some large scale process, maybe the radiation cooling down the troposphere, and that's trying to act to destabilize the atmosphere, and at some point then the convection will kick off. Okay. Now the usual assumption is that there's some kind of equilibrium that is well, you can debate whether it's actually or almost obeyed, but where the idea is that the convective tendencies are essentially trying to balance that large scale forcing. Okay. And by trying to equate the two, you can make some kind of statement about how much total upwards mass flux you need to balance this large scale forcing, and so close your problem. Okay. So that would be the usual way to try and get the system closed. Okay. So let me start just by saying something about bulk models, because I started writing down equations for kind of little subscripts for each particular cloud, but it's actually quite rare for somebody to kind of go and figure out what's going on in each particular cloud. They tend to get lumped together into a bulk kind of effective cloud. Okay. So this is what's usually done in practice, and it's certainly a lot cheaper to kind of do one calculation than 30 or 40 calculations. Okay, so what happens if you start from the plume equations of a typical plume model and just do a summation over plumes? Then what happens is you get back essentially the same equations that you first thought of. They have very much the same kind of structure, except that where we saw something like chi sub I before, we now see this kind of structure here, which is kind of mass flux weighted average of chi, which we can call chi b, a sort of bulk value of chi. And the total amount of mass flux is just going to be the sum over all the mi's. So we end up with one kind of bulk plume, effective plume. Okay. So that's the idea. And life is just now much simpler. Okay. Okay. It doesn't, this kind of doesn't quite come for free, right? Okay. I mean, there is a price to be paid in the sense that the plume equations are not quite linear. It works well, it would work nicely if everything was linear. But something, I mean, for instance, that you've got to decide where the tops of these clouds are. Right, so where the buoyancy vanishes, and this is kind of a switch function. Right, your cloud will just stop at the top of the cloud. So, in fact, if you work it through to make this kind of work, you need to make an extra, what was originally called a gross assumption. I don't know. I prefer just to think of it as an ansatz. You have to say that something about the detraining cloud liquid water. You have to set it equal to the bulk value to make this system work. Okay. So that appears in one sentence of a paper of Yarnai et al. 1973. Okay. It seems to me it's largely been forgotten, and lots of people will start their description of their parameterization by writing down a bulk model. Okay. But I kind of just must. I think it's kind of worth repeating actually, that you kind of assume that everything is linear, and there's a price to be paid for this. Okay. So where it's usually forgotten is that you're also kind of assuming that the microphysical terms that you put in, they will need to be linear for this to work, and cloud radiation interactions between the cumulus and the radiation, they will have to be linear as well. Okay, they're supposed to be if you're using a bulk model. That's okay. Now you may well decide this is a price you want to pay. Okay, but it's just the kind of point that cumulus microphysics tends to be very crude, but actually it's supposed to be very crude in the models. Okay. Okay. So that's kind of, I mean, there are arguments you can have about using a bulk model where kind of dividing into. There are advantages of the bulk model in the sense that you might find it easier to specify entrainment and detrainment rates, for instance. Okay, so it's not a kind of, I'm not trying to make a big argument against bulk models, but I think we should be aware of the limitations. Let's kind of now deal with the fact that we don't have an infinite amount of clouds in the box, see where that leads us. Okay, now it's fairly easy to convince yourselves of that, just from kind of rather simple scaling arguments. So a typical mass flux for any one cloud, you can observe this or just look at your kind of cloud resolving model data or something, around about 10 to the 7 kilograms per second. And to balance a typical kind of forcing rate, you're going to need a mass flux of around about 10 to the minus 2 kilograms per second per unit area. Okay, so the amount of clouds you expect to find is something like 10 to the minus 9 times area, on the order of 10 for a typical GCM grid box. So that's around about 100 kilometers. Okay, so 10 is not equal to infinity, and we ought to perhaps worry about that. Okay. And in particular, it's kind of easy to show from for example, coarse graining some of these very high resolution simulations that Tim and Glenn have talked about. But the number of clouds in the GCM group is essentially not large enough to give you a steady response to a steady forcing. Okay. So the subgrid scheme should not live in the same state every time you look at it, even if you've got the same kind of continual forcing. Okay, let's see if we can say something about that. We'll kind of keep the equilibrium assumption for the moment, which essentially is going to give us the ensemble average mass flux at cloud base. Okay. But if we want to think about the variability that's going to come out of having a finite number of clouds, we have to essentially consider the partitioning of this into individual clouds. Okay. So one way to get at this will be to look at the PDF for the mass flux in a single cloud and the PDF for the number of clouds present. We stick the two together, and essentially we've got everything we know that we want to know. Okay, now the kind of big insights into this kind of thing that Cohen and Craig pointed out was just really to recognize that all the assumptions we've been making about the clouds as kind of discrete, individual, non-interacting, point-like objects in some sort of equilibrium with a large-scale macroscopic state are directly equivalent to all the assumptions you make about talking about an ideal gas. Okay. If you change the words around, you're essentially talking about exactly the same kind of system. So from that, it turns out that the PDF of the mass flux per cloud must be a Boltzmann distribution, just in the same way that you must have a Boltzmann distribution for the PDF of energy in each gas particle in an ideal gas. And in fact, this turns out, if you look in CRM data of a number of sorts, it turns out to be really remarkably good. Okay? Even in situations where you're kind of starting to doubt these assumptions from the design of the experiment, this still seems to work very, very well. I've yet to see an example where you don't get a good exponential distribution out. Okay, it's really a robust kind of feature. Okay, so what we're actually after is the PDF for the total amount of mass flux at cloud base in order to close our scheme. Okay, so here we just say that number of clouds is not fixed. Okay, so that's the real difference from an ideal gas. Clouds can just appear at random. You've got a steady kind of number. But if they're not interacting with each other, then the number that we observed in some sort of finite sized region must be just a Poisson distribution. And if we convolve that Poisson distribution with the PDF of little m, essentially we get the PDF of big M, the total amount of mass flux. Okay. And again, you can kind of test this in your CRM experiments, and it kind of works remarkably well. Okay, so the histogram just comes from some CRM data for this. And let me see, these are essentially just different methods of trying to fit that curve.
Poisson usually means each entity is statistically independent of each. If I'm a cloud here, why would I be independent of my neighboring clouds? Whether I switch on or not, as it were.
Well, I mean, in reality, you're not, right? But that's the kind of traditional assumption that's made anyway.
Okay, so you're not defending it, you're just
No,
using it
no,
for
no.
simplicity.
Exactly. Yeah. But I mean, you seem to kind of get away with it, at least in some situations where the clouds are not packed too closely together. We'll come on to kind of trying to back off for that assumption in a minute. Okay, so there have been various arguments about stochastic parameterization, why it might be useful, what effects it might have. For me, actually, in this kind of framework, it's that there's no more argument needed than other than it's absolutely the natural thing to do. Right? So we've been talking about the finite number of clouds. It kind of seems crazy to kind of use a deterministic parameterization. But if you want to be deterministic, you're essentially assuming your grid box size is equivalent to the large scale state, and there are many, many clouds in that state. Okay? If that's not true, if you slide delta x along this axis, then essentially you'll see fewer and fewer clouds, and you'll just see fluctuations about the statistical equilibrium state. Okay. So all I'm saying really is your parameterization really ought to have some sort of idea where it's living on this continuum and be able to react to that appropriately. And kind of important point to note is that none of these scales is necessarily has to be fixed in your numerical simulation. So what we're saying, the convection on the large scale we assume to be kind of parameterizable in the sense that we can just use a deterministic scheme, but if you look on any smaller scale, you will just see fluctuations around that. But you know what the PDF for these fluctuations is, so you can just sample from that and derive your parameterization that way. So I'm not going to go into kind of gory details of the parameterization we wrote, but you can indeed write a parameterization that will implement exactly this idea. Okay. I just kind of show one plot to kind of show that it does have some impact and that it's not just it's not just all washed out or a waste of time. This is kind of just a single column model. We're looking at the ensemble spread in temperature. The red line is random variation of parameters, taking the scheme from the kind of standard Met Office scheme for doing this that we just stole. This is what happens if you run this stochastic parameterization, and of course the answers depend on what size you assign to your grid box. Okay. So for a 100 kilometers grid box, there are actually a fairly large number of clouds in there, and the spread is kind of relatively low. For a grid box of 50 kilometers or so, the spread from kind of these statistical fluctuations comparable to kind of variation in parameters. Okay. If you look a bit, I'm not showing plots for this, but if you can kind of compare the 50 kilometer run to a deterministic version of the same scheme, you'll see that there's a stochastic drift in there. This is on the scale of switching between one deterministic parameterization and another. Okay, so it's not enormous, but there's certainly a drift in there. Okay, so I said I would say something about spatial correlations then. This idea that actually the clouds might care where the other neighbouring clouds are, and they're not all completely independent and non-interacting. Okay. So in a sense we're talking about how the clouds get organised. So far we've assumed everything to be kind of completely random in space, but in reality, we kind of, a quick glance at the satellite image will tell you that convective clouds readily organise themselves into large-scale features. Okay. Now, of course, this will affect both the mean response and it will affect the variability. Okay. And, well, the question is, can we say anything useful about this? It seems to me we kind of can. Okay, so first of all, I'm just going to plot again from the cloud resolving model results, give you some idea of kind of what this non-randomness looks like, if you like. Okay, so imagine we're setting a particular cloud and we move a certain distance away, and we can ask how many other clouds will I see within a radius of that distance. How many clouds are near to me, and we can compare that to how many I would expect to see in this area if the clouds were completely randomly distributed. Okay. So we normalise this, if you like, spatial correlation function to 1 for a random distribution. And what you'll see is that this is coming out of a CRM simulation that's been run out to equilibrium with a completely homogeneous forcing in the horizontal. Okay, so this is complete self-organisation. There's no organisation being imposed on this at all. But I mean, you don't get a kind of massive effect, but for round about sort of 10 to 20 kilometres, you see that the clouds tend to clump together somewhat. Okay, they tend to group together on those kind of scales. And actually, how effectively they do it depends on what kind of boundary conditions you impose at the surface, whether it's an SST boundary condition or whether you impose fixed surface fluxes. It's kind of an interesting point. Okay. So this kind of gives you some idea what can go on. I mean, of course, if you've got a more complicated large-scale flow, they can organise into much larger scale features. But this is the point for me is that this is a subgrid, right? So how do we handle organisation when the organisation is taking place on the grid scale is not the problem I'm going to consider now. But this is definitively an organisation process that's happening on the subgrid, and so it's clearly the business of the parameterisation to do this job for us, to try and take any account of this if it's important. Okay, how do we do this? Well, it's actually not so hard to do this. So essentially all we're saying is that we've got something that looks a bit like an ideal gas, but now the clouds are kind of interacting with each other a little bit. So essentially we just invented a non-ideal gas. Okay, and there are lots of methods to analyse what's going on with a non-ideal gas. Okay, so long as the interactions are reasonably weak, they don't structure, the clouds don't kind of correlate too much, then we can consider some kind of perturbation expansion, right? And we only worry about pairwise interactions between two clouds in this limit. And if that's the case, it's just like saying that we've got each cloud being subject to an interaction potential that actually we can get straight from this spatial correlation function that I showed you on the last page. So, what would be the effects of that? Well, we can kind of calculate the effects kind of using your statistical mechanical methods. One thing to look at is just the expectation value of a certain mass flux m, given the fact that we know that there are n clouds in the region. This is the formula for that. So this is kind of rather like the equation of state, and we just have this term at leading order if the clouds were not interacting at all. The interaction is kind of this piece out here, so it depends on how closely things are clumped together, and it also depends on this spatial correlation function we've been talking about. So at this point I'm not going to be able to prove to you whether this formalism works very well, okay, because there haven't really been systematic studies to kind of see if we can pick up these effects. So best I've managed to do is just to find a slide from Davudi's theorem data. This is this conditional average of given that we know how many clouds are in the region. It's plotted at certain different heights. The straight line here would just be the expected value. The expected value for everything being non-interacting, and please ignore the error bars, which aren't really error bars. And okay, I wouldn't have put these on. They don't really have a combination of error bars and something else. But anyway, I guess what if the point is that as we go to larger and larger n, this is where you see the deviations away from this. So that's kind of consistent, and they're kind of at least consistent in sign. If you get clumping, we expect it to decrease in this direction. Okay. So it's a kind of hint that there might be something in this, but I wouldn't want to put it any stronger than that. Okay. Well, similarly, we can look at the variance. So let's look at the number variance. The correction here is again based on an integral over this spatial correlation function, and if the clouds are kind of clumping together, the potential kind of attractive in a sense, then this will be a positive contribution. So what we conclude from that actually is that the system we looked at before, where we assumed everything was non-interacting, we're probably making some moderate underestimation of the variability. Trying to kind of throw numbers in based on this W12, I say we've not really been studied terribly carefully what that is, but I would say this is probably on the order of kind of 15–20% for this kind of clumping over 10 to 20 kilometres. There may be other modes of organisation. Okay. So the point I get to take from this then is that while this organisation is kind of perhaps not critical to take account of, at least we kind of have a framework for doing that if we want to. What we would really have to do is to kind of understand this W12, this spatial correlation function. How does that vary under different circumstances? Okay. That's what we have to get a handle on if we wanted to include this in a parameterization. I don't say we have to, but that's what we would need to understand if we were to include these facts. Okay, so we've got so far in kind of removing some assumptions. Let's see if we can think a little bit about time dependence now, this kind of equilibrium assumption. Now, people have tried to play with this, the idea just being that sometimes there might be relatively rapid forcings, let's say the diurnal cycle, where it's not a priori obvious that you're going to be in an equilibrium. So people have kind of, played around with these things, but in a very ad hoc kind of way, it seems to me. And to me, actually, the rather more important question is that even for a steady forcing, it is not immediately blindingly obvious to me that you have to get to an equilibrium. And even if you do, it's not immediately blindingly obvious what this equilibrium looks like. There may be several of them that are possible. So that's the kind of thing I want to think about now. Okay, so what's the kind of system we look at here? First of all, the kind of source, the kind of potential energy that the clouds are drawing on, you can kind of estimate by something I call BI, which you can kind of imagine as just being a vertical interval of buoyancy through the depth of the cloud. Okay, so if the cloud is not kind of doing any entrainment, detrainment, this is what people would typically call the cape. Okay, so it's just a glorified version of the cape if you're familiar with that. It's essentially some available energy that's available to that cloud type. Okay. And if you take the derivative of the formula you write down for that, put in your cloud model, do some algebra, or alternatively look in the appendices of Arakawa and Schubert for it, what you'll find is that the time dependence is driven, it looks something like this. There's this term Fi, which essentially encodes all the large-scale forcing processes that are acting to destabilize the atmosphere. Then you've got this term M, so this says that the convection, when it kicks off, will act to reduce this available energy, it'll convert it. Okay, and there's some kind of constant factor out here, gamma, which essentially encodes how effective is each particular cloud at removing this instability. Okay. Similarly, we can kind of write down an equation for the kinetic energy in each cloud, or at least what we think are the dominant terms in there. And that is essentially saying that the kinetic energy is being driven when this buoyancy is being converted by the mass flux. That's what generates kinetic energy for us. And it's also kind of being dissipated over time on some time scale that we'll call tau d, typically taken to be on the order of an hour. Okay. So this is essentially, when we're thinking about prognostic system, this is the equation that people would start from. Okay. Problem is, of course, that we've kind of got three things we're talking about here, the Ki, the Mi, and the Bi, and only two relations between them that anyone's happy about. So, what was kind of done in the mid-90s is to say, well, look, this Ki goes like W squared, and this mass flux goes like W. So let's see if we can assume that the kinetic energy just goes like the mass flux squared with some constant out the front. So, certainly do that, and you can write down then the resulting equation for Mi, which turns out to look just like a damped harmonic oscillator. Very, very boring. Okay, so you start from some initial condition, you'll tend towards your stationary solution. It'll take you something on the order of a few t times Td to get there. Okay, so something on the order of a few hours to reach the equilibrium. So that seems fine. I mean, at that stage, everybody kind of feels fairly comfortable about this, that we can reach the equilibrium fairly quickly, and it's going to be a reasonable approximation. Now, to my mind, there's just kind of one thing wrong with this, which is that it's wrong. Okay, so this assumption that Ki scales like mass flux squared just does not work. It doesn't kind of match up with the scalings that you observe. If you run a cloud resolving model, let's say, with a steady forcing for a long time, look at it in the equilibrium state. Okay. If you double the forcing, then essentially you double the mass flux. Okay, you need twice as much response to this forcing. But that can be achieved in different ways, right? You could achieve that by doubling the typical values of vertical velocity. You could achieve it by doubling the typical values of the fractional area covered by cloud. You could achieve it by any mixture of those two things. Okay. Now, In practice, there are kind of scaling arguments and CRM data both say that the effect on the vertical velocity is going to be rather small. Okay. And here we kind of see an example of this. The forcing is kind of ramped up by a factor of 4 in different steps. Typical vertical velocity is changing by around about 10%. Typical number of clouds changing by a factor of almost 4. Okay. So if you like, the response to more forcing is to have more clouds. The clouds look more or less like they used to with the weaker forcing. Okay. Clouds are clouds are clouds, but you have more of them when you force the atmosphere harder. To a first order approximation. So the way to respect that is actually to choose Ki to be proportional to Mi. Okay. And in fact, I'm just going to write down Ki as Mi to the power of P, and we'll look at 1 or 2 different choices of P here. Okay. I'll give you results for a bulk system, so there's only going to be one cloud type in here. You can drop all of those I and J subscripts. Okay. So here on the left you see the case P equals 2. This is the initial condition. You're looking at it in kind of M, well, I called it B, didn't I? But the kind of mass flux cape space. Here's the initial condition. Here's the final condition. It's rather boring. You get there fairly quickly and straightforwardly. Okay. Now here's the case P equals 1. And this looks a little bit more problematic. So here's the initial condition. And we simply execute limit cycles around about the equilibrium with an amplitude that basically depends on how far we were away from it to start with. So we're not going to reach the equilibrium state. So this is now looking somewhat problematic. This is not looking terribly realistic of me to say we will never reach the equilibrium state. However, if we play around with this power, see that the kind of choice of 1 is clearly in some ways rather very special kind of choice. If we try 1.01, do a tiny bit more, okay, then we do spiral in towards the equilibrium state, and if we try ever so slightly less than 1, then we basically spiral out and the whole solution blows up. Okay. If P is only just slightly less than 1, it will take us really quite a long time to reach equilibrium. It won't be on the order of TD. Okay. But actually this kind of works, right? So it's somewhat reassuring to know that this kind of, if you like, 10% change is going in the right sense. We don't need much change in vertical velocity to be on the right side of that 1 line. Okay. And the sense in which this kind of linear scaling that I kind of proposed doesn't quite work is actually what's putting us on the right side of being slightly greater than 1 and actually reaching an equilibrium. It's kind of interesting though. It kind of suggests it's kind of if this holds together, it kind of suggests it really is worthwhile in trying to understand this kind of even 10% effect, because this is what's controlling how fast we reach equilibrium. How fast this kind of scaling doesn't quite work. Okay. Okay. Last part then. What I'm going to do now is to truncate this prognostic system. Okay, I haven't made any decision about what P is yet, but let's just kind of truncate it and assume that we can just look at the kind of slow response and hope that we can get some kind of idea about that by throwing away terms that look like d by dt squared and d2 by dt squared. Okay, so I'm just going to keep dm by dt and throw away everything that's kind of faster, if you like, looks to be higher order. Okay, so this is then the equation that comes out. Now, one thing you will notice here is actually just what we were talking about earlier, which is that the factor P appears only in one place, and it appears here, and you'll see that you could absorb it into the definition of what you're calling the time, if you like. You could just completely rescale the time, and that the time scale to get to your equilibrium is going to depend very much how far away from 1p is. Okay, so that's kind of consistent with what we were saying before, really. It's kind of an explanation of why the difference of p from 1 is actually controlling the time scales. Now, for similar kind of argument reasons as we were making before, it's reasonable to say that the mass flux for one cloud, for one type of cloud, is just the max flux for a cloud of that type times the number of clouds you've got. And if you do that, you can write the equation in this form. That's kind of critical. Now, it's a equation that may look familiar to some people. Anyway, you've got this kind of dm by dt, positive number times n, minus something ni and j. Okay, so in fact, what's known as the Lotka-Volterra equation is an absolutely standard page 1, chapter 1 ecological kind of system. Okay, it's a kind of foxes and rabbits kind of system, predator-prey system, or depending on the signs you choose, it's different animals competing for the same resource. Okay. It's kind of an interesting analogy. Okay, so I guess what you're saying is that here the resource is, if you like, the instability that's being built up by the forcing, and different cloud types are able to compete for that in different ways. Okay. So in practice, we would kind of expect the shallow clouds to be kind of really quite effective at removing the instability, but then the very deep, big thunderstorm clouds are kind of, if you like, niche animals in this ecosystem, right? Because only they can access the instability that's at the top of the atmosphere. Okay. So as I sort of point out, this kind of system has been kind of extensively studied by ecologists. You can pick up entire textbooks that are just about this system of equations. So if you're still buying this as a kind of model of clouds, it's nice to kind of think about an example of how you might actually use this in practice. Well, let's for simplicity just consider two cloud types. Let's consider the shallow clouds and the deep clouds. Okay, so there's only two here. Now, if you look in your GCM, there are probably going to be two parameterization schemes, or if not, there's at least kind of a switch somewhere in your convection scheme that says, I want to treat the shallow kind of convection differently from the deep convection. And the criteria for deciding whether we're in a regime of shallow convection or deep convection is going to be actually rather ad hoc if you look at it. Okay, it's rather ad hoc, rather empirical. You certainly don't see that much consistency between different models. And more generally, simply transitions between shallow and deep regimes are just not well understood. Okay, they're not well captured by the model. People don't really understand how those transitions kind of work. Okay, so let's see what we can do with this kind of system. Well, the kind of thing that's already been done with it is to say that for that system with just two types, your equilibrium states essentially consist of this. Either everything goes extinct, right, or one of the cloud types, one of your animals goes extinct and the other one kind of stays around, right, or both of them hang around. Now, which of those equilibrium you reach, you can kind of also argue depending on what those parameters look like. And in particular, there's a globally stable equilibrium, right? It doesn't matter what your initial conditions are. And the globally stable equilibrium with both of the cloud types is kind of satisfied if these conditions hold on your parameters. Okay? And if these conditions won't hold, then if you wait long enough, one of these two types of animals will be kind of get driven to extinction. So here is kind of what I would suggest if we've got if we stick to an equilibrium-based closure, equilibrium-based parameterization, right, then it's almost a kind of self-consistency kind of check on what type of shallow or deep cloud we've got. Right? We don't have to kind of introduce any ad hoc new numbers. Right? All we have to do is evaluate these things, which will depend on what our cloud model is, but given a cloud model we can evaluate all of these numbers. Right? We then test the inequalities, and that tells us whether we should be calling the shallow and deep convection schemes together or not, or just one or just the other. Sorry, so this will be the forcing for cloud type number 1 and number 2, yeah. So that remains to be said. That's the kind of proposal, I guess. I mean, again, this is very much in the realms of a rather speculative kind of talk, right? I have yet to confront this with any data. But, it seems to me, I think the argument I'm mainly trying to make is it's actually kind of worth studying these systems, right? Not just look at your kind of standard equilibrium-based closure, but to kind of try and extend it. Okay, because it's actually quite possible to learn something. It doesn't mean you have to kind of move away from a equilibrium-based closure necessarily, but it does kind of seem to impose certain constraints that we ought to think about. Okay. All right. Okay, if you're still with me, then the next kind of few minutes you just have to kind of really indulge me as to kind of a little bit of speculation. But I kind of can't resist it. I can't resist it mostly for the reason because I've given quite a lot of talks where the title of the talk is a question, and I can't remember ever actually answering the question before. That's fairly kind of normal. You know, you give a kind of question, you talk around it. But I'm actually going to suggest something that might be a useful framework, where you can write down a model that's not a bulk model. It doesn't require that there are large n. You can consider the clouds to be interacting. You can consider time dependence. It's fine. I've not actually built the model, but I just explained that. I just want to make the case that such a thing can exist and it can be built. Okay. So the prognostic systems, in the prognostic systems, we were assuming that there were an infinite number of clouds again. Right? Maybe I didn't state it very explicitly, right? But we assumed essentially that I could write down things like dn by dt, and that meant something. Okay? So that n was a continuous variable, practically, and so there must be a very large number of clouds around. So the question is how to generalize this further to get a finite number of clouds. And again, remember, we want to kind of keep the kind of things we know as a kind of limiting case of this. Okay. Well, I'll tell you what the model looks like. It would be kind of very, very sketchy, but the kind of big point, I guess, is the kind of methodology has been explicitly followed through for kind of biological cases. It looks something like this. And I can show the article where they've done that if you like. What you do is you think about an individual-based model, so you think about a model for kind of individual elements, okay, and there's going to be a difference equation for the probability distribution of the state of that model that evolves according to some specified transition probabilities that essentially decide things like, am I going to generate a cloud of type I, am I going to remove one, if there are two clouds of type I and J's, do I put another one in of type I or type J, or do I remove one, or what do I do? Okay, so you have to write down various transition probabilities of that sort. But if you do that carefully enough and you choose those probabilities right, then what you can show is in the limit of a large system size, you recover precisely the deterministic ODEs that you started with. Okay, so that's really kind of the property that you want to have. Okay, so we're basically making a kind of stochastic individual-based analog to the deterministic parameterization. Okay, there's something called a Van Kampen system size expansion, which is formally what you're doing here. Okay. Now, the leading then correction for a non-infinite system basically turns your ODE into a stochastic differential equation and accounts for the fact that there will be fluctuations in the number of clouds around. So that's the kind of interesting way to kind of study that system as well. Okay. And in fact, if you look at these kind of systems, actually, it's that is actually the hard part to kind of write down this probability. These sets of probabilities that will translate into your ODE. But once you've got it, it's actually very, very straightforward indeed to generalize it onto a lattice. Okay. And if you want to think that these clouds interact and that the spatial dimension matters as well, then you just modulate those transition probabilities you first thought of based on what you think the spatial correlations are going to be. So you can kind of build a model if you want. I stress the point where we're getting speculative here, right? But instead of having a bulk, non-interacting, infinite n, non-time dependent model, we can consider a model with all of those things wiped away, and in which the kind of standard picture is some limit of that model. Okay. So, I guess another way to look at it is all of these things are parameterizable if we want them to be. Right? It doesn't mean that it's a good idea to parameterize them, but in principle all of these things are parameterizable. Okay. Not as much as I wanted to say. As I say, it's kind of a little bit speculative, and I haven't actually built this model yet, but the point is that you can do. Partly actually I throw it out there to see how much ridicule it gets, okay, before I actually try to, to do the work. Well, this in some ways is kind of what I've said. So the typical convective parameterization, if you go and look at the code for it in your GCM, will be based on a bulk model of entraining and detraining plumes. Okay, that's the normal thing to do. If the grid boxes are not large, and remember I think something on the order of 50 kilometers is not very large, okay, then the fluctuations about a statistical equilibrium will be important, and they do kind of contribute to stochastic fluctuations in your GCM. If you feel that the cloud-cloud interactions are important on a scale that's sub-grid, you can account for those, but I mean the hard part is that you really are going to need to kind of design some very careful experiments and really understand this spatial correlation function, which nobody is kind of really trying to do in any kind of systematic way. But you can incorporate that into the formulas. Okay. I would argue that it's worthwhile to look about these the kind of outer equilibrium systems. Not necessarily because we think that the kind of the forcing is so fast that you can't reach an equilibrium, but you kind of, by asking about, almost by insisting that you reach an equilibrium, then you can kind of impose certain constraints on what's going on that may well be useful. And as I say, I kind of proposed a framework for the kind of all singing, all dancing kind of model, which I would suggest would be kind of useful intermediate kind of model to study potentially. Okay, so we kind of hear this in climate modelling a lot of the time. You've got your great big all singing, all dancing GCM that where you throw the kitchen sink at it. At the other extreme, you've got your some kind of simple radiative energy balance model. Okay, there's a lot of a lot of models that try to sit in the middle and try and get some insight into what's going on. You very often kind of consider a model that's somewhere between those two extremes. So all I'm really suggesting is that actually a similar kind of thing is going on with the problem of your subgrid parameterization. Right? If you look at something like a cloud resolving model, then this is a kind of hideously complicated beast that contains all sorts of nasty microphysics and all sorts of complicated things going on. And that's kind of one extreme, right? The kind of traditional standard bulk plume model is almost the other extreme, and what I'm almost proposing is some kind of model that sits in the middle, right? As a way of trying to understand something about these two models on the other extremes. Okay. Yeah, and that was as much I want to say, so thank you for listening to my speculation.